Where we left off, we had just finished defining what a molecule is, which is a group of atoms held together in stable formation. The next concept that we need to tackle is how molecules form. Molecules are created when two or more atoms transfer or share their electrons with each other. When this transfer or sharing of electrons occurs, we now say that a chemical bond has formed between the atoms involved. But there's an additional layer of complexity, which is that these bonds are categorized in one of two ways, depending on whether the electrons are being transferred or shared. When electrons are transferred, meaning one atom takes electrons from another atom, the two atoms involved in this transfer gain opposite electric charges. One becomes positively charged and one becomes negatively charged. Because remember, the electron particles have a negative electrostatic charge. So an atom that takes an electron becomes negative, while an atom that loses an electron now has an excess of protons and is positive. So the particles now have this linked attraction to each other. The opposite charges attract, sort of like magnets. As a result, a molecule is formed. In this case, we have a molecule of sodium fluoride consisting of one sodium, indicated by Na, and one fluorine, indicated by the letter F. They completed the transfer of an electron, and now they are held together by an ionic bond. And once this happens, we actually no longer call the sodium and fluorine atoms. Instead, we call them ions. Ions are atoms that have gained or lost one or more electrons, and so now they have an electric charge. There are different types of for there are different types of names for ions depending on whether their electric charge is positive or negative. Cations have a positive electric charge due to having lost a negatively charged electron, while anions are the ones that have a negative electric charge due to having gained an electron. This is a little backwards from what you might expect. Gaining an electron makes an ion more negative, but that's because the electrons have a negative charge. So in this case, sodium loses an electron and becomes a positive cation, and fluorine gains that electron and becomes the negative anion. But as we said, transferring electrons is just one way that atoms can become chemically bonded to one another. Atoms may also share electrons with each other rather than transferring them. And when this happens, the chemical bond that forms is called a covalent bond. Any electrons that are shared will become part of the outer orbital of both atoms involved in the arrangement. Okay? Um, so in this example, we have two atoms of chlorine. The atoms will come together and they both bring one electron to the table, and they form a covalent bond, where this pair of electrons belongs to two separate orbitals. It belongs to the orbital of the chlorine on the left, and it also belongs to the orbital on the chlorine on the right. So we've established that there are two types of bonds: ionic bonds, where electrons are transferred and create electrically charged ions that are attracted to each other, and then covalent bonds, where two atoms each bring electrons to the table and they share with each other. So the electrons become a part of both atoms' orbitals. But how do we know which bond will happen in any given situation? Well, this has to do with the identity of the elements involved. What you're seeing here is a periodic table that has been color coded based on what each element is: a metal, a nonmetal, or metalloid, which is a substance that has some qualities of metals and some qualities of nonmetals, a metalloid. We just want to focus on the metals in silver and the nonmetals in bronze. Some examples of metal elements you can see in this metal section are aluminum, zinc, iron, cobalt, and nickel. Some examples of nonmetals are hydrogen, carbon, nitrogen, oxygen. Oftentimes, from our experiences in the world, we can tell from the name if it's a metal or nonmetal. Elements are quite electron greedy. Because of this quality, they will take electrons from atoms that are willing to give them up. The elements that are willing to give them up are the metals, because metals are not so electron greedy, and they readily give their electrons away. So when a nonmetal forms a bond with a metal, it will be an ionic bond because a transfer of electrons occurs. When a nonmetal element forms a bond with another nonmetal element, however, they are forced to share with each other because they are both greedy and both want electrons. So neither one is willing to fully give up their electrons. So nonmetals form covalent bonds with other nonmetals. So we said that nonmetals are more greedy than metals. However, not all nonmetal elements are equally greedy. And when they get together in a covalent bond with another nonmetal, the comparative level of greediness between the two elements in that bond also affects its qualities. When you have a bond between two nonmetals that are equally greedy for electrons, we call this a nonpolar covalent bond. These types of bonds form when two nonmetals get together, and those nonmetals have very similar levels of greediness, so they share electrons equally. A great example is the one that we just looked at. Two chlorine atoms form a nonpolar covalent bond. Obviously, because they are the exact same element, they have the exact same level of greediness, so they end up sharing those electrons equally because they are each tugging on them with the same level of force. Now let's take a look at what it looks like when two nonmetals get together and share their electrons in a covalent bond, but one of the elements is more greedy than the other. We call this type of bond a polar covalent bond. The electrons are still being shared, but they are not being shared equally. And this is because one of the elements involved in the bond is greedier than the other and is tugging on those electrons more strongly. An example of two elements that would engage in a polar covalent bond are the uh, elements hydrogen and chloride. It turns out that chlorine is more electron greedy than hydrogen. There's a disparity there. So when they enter this arrangement, they will share those electrons, but chlorine will pull them closer to itself and away from the hydrogen atom. As a result, the right side of this molecule is now slightly negative because it has more of the negatively charged electrons, while the left side is slightly positive because the electrons have been somewhat drawn away, leaving the positively charged protons to predominate. That's why this is called a polar bond. When we think about the word polar, what it means is there are two opposite ends, the North Pole and the South Pole. These are the polar opposite ends of the Earth. In this polar bond, there's a positive end and a negative end. This is why we call it polar. And we can see here the slightly positive end on the hydrogen versus the slightly negative end on the chlorine. So to summarize, we have three types of bonds that are formed between atoms when they become molecules. In ionic bonds, electrons are lost from one atom and gained by another. And these types of bonds occur between an element that is a metal, which gives up its electron, and a nonmetal, which receives it. Covalent bonds involve two nonmetals sharing their electrons, and there are two types. In nonpolar covalent bonds, the elements have similar levels of electron greediness, so the electrons are shared equally because they are both pulling on those electrons equally. In a polar covalent bond, there is a difference between the electron greediness of one of the elements and the electron greediness of the other. One pulls harder on the electrons. So you end up with an unequal distribution, and one end is positively charged, the other is negatively charged. This might seem like we are getting far into the weeds here, but these principles about different types of chemical bonds are going to be very important on the next page of content when we talk about the role that water plays in supporting life on Earth. So keep them in mind for that. Before we have that conversation, though, there is another topic that we need to cover that is closely related to chemical bonding, and that is oxidation reduction reactions. Oxidation reduction reactions are a specific type of chemical reaction where one or more electrons is transferred between atoms or molecules. Oxidation reduction is kind of a mouthful to say, so they are usually abbreviated as redox reactions. The most common, simplest redox reaction is the formation of an ionic bond between two atoms, which we have already seen. Let's take a moment and discuss why they are called oxidation reduction reactions, because understanding what this name actually means can make it easier to remember what these reactions are. First of all, what is the meaning of oxidation? Well, this part of the name derives from the element oxygen. Oxygen is one of the most electron greedy elements, and so when it engages in chemical reactions, it often takes electrons from other atoms or molecules. As a result, the atom or molecule that has lost an electron has become oxidized or acted upon by oxygen. However, it's important to note that the element oxygen is by no means always the thing taking electrons. It's just so notorious for its electron greediness that it gets its namesake um, and use case. So that's one half of the equation. What about reduction? Reduction gets its name from the fact that electrons have negative electric charges. So when an atom or molecule gains an electron, it actually experiences a reduction in its electric charge because that charge becomes more negative. So that's oxidation and that's reduction. And the two are always coupled with each other because a molecule can't lose an electron without another molecule taking it. If you have an oxidation take place, you inevitably have a reduction taking place too. But now that we understand the origin of the redox reaction name, this brings us to the bigger question of why do we care about redox reactions? Why does it matter? Why are they relevant? Well, every molecule has a certain amount of stored energy, and the subatomic particles that carry that energy is the electrons. This sort of makes intuitive sense if you think about what you know about electricity. For example, an electric current. The electrons drive the movement of the energy in that electron current. So when a redox reaction takes place, that represents energy being moved around, not through a wire like a circuit, but by jumping from molecule to molecule. Not and the transfer of energy between molecules is going to be an important concept for understanding how energy moves through food webs and also for understanding how nutrients are cycled through the biosphere. This is a concept that will be coming back to us several times throughout the course.